Hi there, this is Penelope. This is the recorded version of the live video that you would have had Friday 14th of May 2021, and it's the first class in the topic of vectors. Now it does assume that you've watched the main teaching video, the one that's available on Podia, because without that this won't make much sense. So let's get started. A lot of the problems that we're looking at here are straight out of the textbook, but there is still plenty more in the textbook for you to do. Okay, the first one, drawing a diagram always helps. So we've got 15 meters per second at 48 degrees. And we've got to decompose it, resolve it, whatever, into the two components. So the x component, this is all just based on trig, will be 15 cos 48. That's roughly 10. And the y component is 15 sine 48, about 11.5. No, 11.15. The second question on the slide, again, draw a diagram. We've got one force going north, so that's to there, and then another one going this way of 4. So I've got some sort of resultant in there. Calculate the magnitude and the direction. The length, the resultant, is going to be, just by Pythagoras, should be square root of 97. And if we call this angle alpha, alpha is going to be the inverse tan of 9/4. 66 degrees. But not exactly alpha. Really, we should call that, say, something else like theta and make it go around that way, because really we're looking at the wrong angle. Actually, that's not quite right either. Let's take that out. Theta has to be the little angle, so actually theta is going to be 180 minus 66. Which is roughly 113. Again, draw the diagram. 13 newtons, 62 degrees. And x is going to be 13 cos 62, whatever that is, and y is going to be 13 sine 62. Our last diagram on this page, again, draw a diagram, and we've got 12 newtons in that direction and 7 there, and some sort of resultant. So the length of the resultant is going to be, again, by Pythagoras, square root of 7 squared plus 12 squared, whatever that equals. And theta is going to be, now we can always short circuit this, theta is going to be 180 minus tan alpha, sorry, tan inverse of 12/9. 12/7. Okay, so it's 180 minus 59. So just make sure you're in the right quadrant. This is why drawing a diagram is important. Now we're going to move into 3 dimensions. We've got 3 velocity vectors there. Let's have a look at the horizontal bits to start off with. So if we look at, say, the horizontal component for vector 1, that would be 10 cos 30. And for V2, it'll be 0, but we could work it out if we didn't recognize that it was 0. But it will be. And for vector 3, it's going to be 15 cos. Now, it's not 15, it's 195. It's 180 plus 15, which is then a negative number, which you'd expect because it's in the left-hand direction. Okay, so the total horizontal would be all of those added together, and that would be negative 5.8. Now do the same with the vertical. So that's a little bit difficult. I really shouldn't have used little v. So the vertical component is going to be 10 sine 30, which is going to be 5. And the one for V2 would be 20 sine 90, which is just 20 times 1. And for vector 3, it would be 15 times sine 195. And that's a negative number, and that's again expected. So adding them all together, we would get 21.118 meters per second. Now you're asked to find the magnitude of that. So the magnitude of total of the final resultant would be square root of all of those added together. It would be the square root of h squared plus v squared, and that would be negative 5.829 squared plus 21.118 squared, and that gives you 21.9. And the direction, say alpha, is going to be 180 minus, because we kind of know where it's going to be. It's going to be 180 minus tan inverse of v over h, which would be 180 minus 74.5. So 105. Now I'm just going to stop there because I need to insert another slide. Now the really cool thing is here that we could have used complex numbers. And we could have said that the resultant was the result of adding 10 angle 30 degrees and 20 angle 90 degrees and 15 angle 195 degrees. Now remember, you can't add in polar form, so you'd need to convert them to rectangular. That's for the first one. And the second one would be 0 plus j20. And the third one would be negative 14.489 plus j3882. Now, we can add like that, and we get negative 5.829 plus j, not a surprise. And then if we convert that into polar, then we get the answer that we had before. And I'm not going to tell you how you need to do it. You can choose which way you do it. Personally, I'd probably go for complex numbers, but that's fine. We need to talk a little bit about unit vectors, and I'll talk about that in the next slide as well. A unit vector is just got a length of 1. So the question there says, how would you write a vector in the same direction as E, but having modulus 8? Then you would write 8E. So if A has length 4 units, then a unit vector in the direction of A is just going to be 1 over 4A. Shouldn't say that, that's is. And this sort of stuff is useful when we go on to Cartesian coordinates, particularly in a minute, but also in the next class as well. Okay, so a vector has magnitude and direction, you know that. And a vector that has magnitude 1 is a unit vector. So, for example, that is not a unit vector because the magnitude is not equal to 1. And you've seen that a unit vector of A is going to be A over the length or the magnitude like that in the same direction. Now, moving forward, we need these unit vectors because they determine a vector space where we can then write any vector as some linear combination of the unit vectors. And in the video, you'll see that the dot product of 2 unit vectors is a scalar, like it's just a number, and the cross product of 2 arbitrary unit vectors gives you the third vector that's orthogonal or at right angles to both of them. So what we're thinking through here is that we've got our 3 directions. We've got X, make that a bit longer, we've got X and we've got Y and we've got Z. So the unit vector in the X direction, so that's got length of 1, is I. And mostly we don't actually put a little cap over it there. And the same here. And okay, like that. This whole thing allows us that if we've got some vector, I don't know, AB, like that, so that that length then can be AI, and that length there would be BJ. And I can't make those bold, but they are bold. Then it says that we can write that AB is equal to AI plus BJ. That's just how we write it. And we would also write it then, if this is R, if its name is R, then we would write R equals AB. You can write it as a row, but you just have to be very, very careful that you know what you're talking about then, that it's not confused with an ordered pair. So if we have something like this, where we've got, we're calling it R, its name is R, and this length is 5 times the unit vector, and this one is 4 times the vertical, then r is equal to 5i plus 4j, and we could write it as 5, 4. And if we wanted to add say 5, 4 plus 3, 2, then that's straightforward. That's just 8, 6, which we could write if we needed to as 8i plus 6j. I'm not sure how much longer I have, but I will continue until 20 minutes if I'm allowed to. Okay, find the unit vector. Oh, that says 2. Find the unit vector p for the given vector. Now I need to put a little hat there. So the length of p is going to be the square root of 12 squared plus 3 squared plus 4 squared, just nicely equals 13. So our unit vector that's in the direction of p is going to be p divided by the length of p, which would be just 12i minus 3j minus 4k over 13. And we can write that as 12 negative 3 negative 4 over 13, or just straight out 12 over 13 negative 3 over 13 and negative 4 over 13, and it's as a column vector. I'm getting a bit nervous about getting cut off midpoint, so I'm going to stop there and I'll continue in another video, part 2. So TBC.